So we are going to begin a series of integral transform. So we are going to be looking at the two types of integral transform. The first one is the Laplace transform, LT, or the Fourier transform. So we're going to look at the Laplace and the Fourier transform. So we are going to start with the Laplace transform. As you can see, we're going to be using integration to transform a function from its original state to a new function. So with the Laplace transform, we are saying we have a function f of t, and we are transforming this function f of t using the Laplace transform represented by this curly L. We are transforming this f of t to a new function f of s. As you can see here, f here is small letter representing the original function to this new function, which is capital letter F, and this is varied by t. The new function is varied by s, where we are saying f of s is actually equals to the integral from 0 to infinity minus st f of t dt. So this is how we define f of t, which means we can say the Laplace transform of our function f of t. The Laplace transform of our function f of t is equals to f of s, which is equals to the integral from 0 to infinity e minus st f of t. So we are transforming f of t to f of s, and this exponential, you can see that this exponential has the variable s. So this is the exponential that is used to transform this function f of t into our new function f of s, and then we call this the kernel. We call this exponential the kernel. So this is the main idea. The main idea here is we're using integration to transform a function f of t into a new function f of s. But then since we're using integration, so there are properties for the Laplace transform. We're just going to look at two properties of the Laplace transform that you have to know, that you're going to apply in this series. So the first property is linearity, or the linear property. Just like integration, if we are integrating a g of x plus b f of x dx, this is the same thing as a integral of g of x plus dx plus b integral of f of x dx, right? So the linearity, you can expand this right into this format. So we are kind of using the same idea here with the linearity of the Laplace transform. So we are saying if you have the Laplace transform of a g of t plus b f of t, right, this is the same thing as a Laplace, which is our a is a constant, a and b are constant, where you have g of t plus b, we use the curly brackets, the braces, and this is going to be the Laplace of f of t. So this is the linearity property. So we can expand the braces into two terms when you're given two functions like that. So the second property is actually important, and we are going to do a lot of proof to prove it. It's the property of uniqueness and existency. Uniqueness and existency. So we have uniqueness and existence. Uniqueness and existence of the transform. This is very important. This is very important. This uniqueness. This is very important. So okay. So with this one, we first of all, the existence of the integral of the Laplace transform. Remember, if you're looking at a normal integral from a to b of f of x, we are saying for f of x to be integrated by the limits a and b, we are saying f of x should be, in order for this integration to exist, f of x should be bounded by the interval, to be bounded by the interval a, b, isn't it? In order for this integral to exist, such that if we are integrating from 0 to 1, we are integrating probably we are integrating minus 3 dx, right? So this is going to be x minus 2 over x minus 2 minus 1. No, this is x over minus 2, and from 0 to 1. So if we substitute 0 here, you can see that it's undefined. So this function is not bounded between 0 and 1, so you cannot integrate it. So we are saying in order for us to integrate it, the limit has to be bounded within that function. So we are typically using the same idea here with the Laplace transform. So we are saying in order for the Laplace transform to exist, or for the integral to exist, so from, remember we are saying from 0 to infinity of f of t dt. We are saying for this to exist, it has to be exponentially bounded. It has to be exponentially bounded. In order for the integral to exist, it has to be exponentially bounded. So we are saying f of t has to be exponentially bounded. As you can see by the term, the canal, it's exponentially bounded. Has to be exponentially bounded. Okay, so here, this is from 0. So we can write this as f of t has to be exponentially bounded. So this is f of t, some constant m e to the power kt. So this is the this is very important. So let's prove this property. So if we integrate both sides, so if we integrate f of t dt is greater or equals to, so here we have m, so 0 to infinity, and we have e kt times st dt, isn't it? So this part you can factor out m, right? So that you're left with these two exponential which you can combine. We can just combine to get one exponential function, which means we add the powers. So I'm going to have minus s minus k, right? And then t dt. So from here, if you integrate this exponential with respect to t, integrate an exponential with respect to t, so this is going to be minus s minus k t all over minus s minus k, right? From infinity to 0. And from this side, if you substitute your limit, so an exponential raised to the power, so it starts with infinity. So if you substitute infinity here, an exponential raised to the minus infinity, it's what tends to 0, right? Exponential raised to minus infinity tends to 0. So we are going to have 0 minus, then an exponential to the power 0 is 1, right? So we are going to have, if you substitute 0 here, where there's t, we are going to have minus 1 over minus s minus k, right? So this is m, remember we have the m, so minus is plus, so you have m over minus s minus k, right? So this is the integral a minus t f of t dt. It's exponentially bounded. So this is the proof. So we can actually write this proof in words by saying if f of t is definite, and piecewise continuous, on every finite interval, on every finite interval on the semi axis t is greater or equals to 0, and exponentially, which is what we're explaining, that is exponentially bounded. Therefore you have f of t, which is exponentially bounded, is m e k t. This is the exponential part for all and some, exponentially bounded for all and some constants, m and k, right? Because those are constants. We are saying then the Laplace transform of f of t exists for all s is greater than k. So this is what I was proving. This is just the wording of what I was proving here, that the exponential transform is exponentially bounded. F of t it has to be exponentially bounded in order for us to perform a a Laplace transform. So now we are going to look at how we can apply the Laplace transform in different functions of f of t. So let's say now let f of t be equals to a constant. So in our case, let f of t be equals to 1, which means now we want to transform f of t. So the Laplace of f of t, which is 1 in our case, is equals to the integral from 0 to infinity, from 0 to infinity e minus sk 1 dt, right? So let's integrate this in terms of dt. Oh, sorry, this is not k, this is t, because I'm using the original formula. You have to remember this one, by the way. E minus st f of t dt. So I'm using this. So f of t is what? F of t is 1. So integrating this with respect to t, we are going to have, it's way too simple, we're going to have e minus st over minus s from infinity to 0, right? And this one is going to give you 0 minus 1 over minus s, which we're going to get 1 over s. So therefore, the integral of a constant 1 is equals to 1 over s. So we've transformed f of t into 1 over s to a version of s. So again, let's look when f of t now is actually equals to t, right? So we are looking at the Laplace transform of t, right, which is f of t. So this is the integral from 0 to infinity e minus st. So now our f of t is t, right, dt. So we want to integrate this. So as you can tell, we are going to use the integration by parts for this one. So we are going to use integration by parts. So assuming that you know integration by parts, this is going to be t e s t minus s to infinity plus, oh no, it's supposed to be minus integral from 0 to infinity 1 e minus st over minus s dt. So this is it, right? So if you're using integration by parts, so it's going to simplify us to this. So now looking at this one, looking at this term, so when you substitute infinity, this is going to go to 0, right? When you substitute infinity. So that's very important because the exponential power is negative, so it's going to go to infinity. If we substitute 0, t is going to be 0, so 0 times this is going to be 0 again. So we substitute infinity, this part is 0, substitute 0, it's also 0. So we are going to get here, it's 0 minus 0, and then here minus, it's plus, so this is plus, and then I'm going to factor out 1 over s, then this is plus 0 to infinity e minus st dt. And then I want you to remember we already evaluated this, which is this here, this is this, and we know that the evaluation of this is what? It's 1 over s. So this is simply 1 over s times the evaluation of this, which is 1 over s, which is equals to 1 over s squared. Therefore, we can now say that the Laplace of t is equals to 1 over s squared. This is very important. It's very important. So now let's look at when f of t is equals to t squared in this point. So again, f of s or the Laplace of t squared, right, which is equals to f of x, which is equals to from 0 to infinity e minus st times t squared dt. Again, you use the Laplace transform. You use integration by parts because we have two different functions. So if you use integration by part, this is equals to be t squared times e minus st over minus s from infinity to 0, minus integral from 0 to infinity. This is going to be minus, no, it's going to be 2t times e minus st over, let me put it there, minus sdt. So this is how you evaluate if using integration by parts, right? So if you simplify this again, if you substitute infinity, the upper limit into this function, this term will immediately go to 0, right? It just turns to 0. Again, if you substitute 0, t is going to be 0. So 0 times e to the power st over minus s is just going to be 0. So this is 0 minus 0. And then coming to this part, we have a minus here, right? Which is positive. And then let me factor out 2, and so we are going to have plus 2 over s, right? From the integral from 0 to infinity, we are left with t e minus st dt here, right? And then I want you to look at something. We've already evaluated this, right? Which is this part. So this is equals to 2 over s times 1 over s squared, which is equals to 2 over s cubed, isn't it? So therefore the Laplace of t squared is equals to 2 over s cubed. So this is what you get. So I want you to look at something here. I want you to see something from this past functions that you have just done. So here we are saying 20 is equals to 0, which is 1, right? We are going to get 1 over s. When t is 1, this maps to 1 over s squared. When t is 2, this maps into 2 over s cubed, which is the same thing as 2 times 1 over s cubed. So I don't know if you can see here that if we have t to the power n, right, which means this will tend to, okay, let's start with the denominator. If it's 2 here, we have 3 here. If it's 1 here, we have 2 here. If it's 0 here, we have 1 here. So which means this is going to be n plus 1, right? So again, if we have 0 here, we have 1 here. If we have 1 here, we have 1 here. If we have 2 here, we have 2 here. So which means 0 factorial is what? It's 1. 1 factorial, it's 1, right? 2 factorial is 2, which means this is going to be n factorial. So we get this. So now we can just say the Laplace of t to the power n is going to be n factorial s n plus 1. This is very important. So in the next video, I'm going to do the Laplace of an exponential function, the Laplace of trigonometric function, hyperbolic functions, and then we are going to